All right, any questions before we get going? There's like less than half the people that are supposed to be here are here. Okay, yeah, so we're going to pick up where we left off last time. Last time you were just experimenting, work through these steps to get a sense of playing with and understanding how to interact with the genetic algorithm and how, as you change some of those hyperparameters, how they affect your algorithm. Now, it's always hard to tell based on one run, though. When you have a suite of settings, it might be important that you run it a few times to get a sense of how it actually acts, because everything's random, right? Like, you might get really lucky one run or really unlucky. So it's important to run it a few times. And we actually will be talking a little bit about how to do proper comparisons a little later in the semester. But anyways, whenever you change one of these settings and you hit run, try to run it a few times to get a feel for how it affects the results. Another thing I will say, and I brought this up a little bit last time, I think, but I didn't go into details. So it wasn't until relatively recently when they started calling all of these like parameters hyperparameters. Let me make sure it's recording, yeah. Because, so you go back, all of those like tournament size, that was called like a parameter, okay? Something that you can change and it'll affect how the algorithm works, right? But a couple of years back, the word hyperparameter started to take over, and there's a reason for it. Does anyone know why? Does anyone have any idea why? It's kind of funny.
Because you're changing the parameters after the parameters were already set.
No, not quite.
I know my feeling about this, but I don't remember because I didn't care enough at the time, honestly.
So it's because if you go back to like the statistics, for example, right? Who here took statistics? Who here learned how to do linear regression? Okay, well, okay, let me re-ask that question. Who here learned how linear regression works? I mean, like actually works mathematically. Yeah? So you can go prove it to me right now?
I failed the class. So
Oh, all right.
that'll be.
So maybe you a little bit. So
That was one of the classes I didn't fail, but I did fail the class, so don't ask that of me.
So when you do linear regression and you're fitting a line to data effectively, you're looking for like that like slope value, right? And it's the algorithm that finds that slope value, and they call that the parameter. And so when you hit run, the linear regression is actually finding the parameter. But that's like for something like linear regression. But in the world of like deep learning and artificial neural networks, all of like the weights on all of your edges, raise your hand if you really don't know anything about neural networks. Okay, that's fine. It doesn't really matter. But you know, it's all these nodes and they're connected to each other with edges, right? And each of those edges usually has a weight. And they'll call those weights the parameters. But then these neural networks have a suite of things like this, right? Like, well, how big is the network? How many epochs do I want to have it run? And so on and so on. But they couldn't call those things parameters because when they were borrowing from the statisticians, all of the weights would be called like the parameters. So they couldn't call the things like, well, how long am I going to let my neural network run? They couldn't call those settings the parameters. So they started calling them hyperparameters. And so that wording eventually like bled over, like overflowed into like evolutionary computation, where we don't really look for, we're not searching for parameters. A parameter is a fine word for this, but often now people call them hyperparameters, and it's really just a consequence of funny history of how it worked out. But that change actually only happened in like the last decade or so, and it really confused me for a while, because I'm like, why are they calling, that's not what this is, but whatever. What else was I going to say about this?
Most don't call them parameters. I will not.
There you go. That's fine. That's fine. That's what people.
You know what I mean if I say it?
Yeah. I feel like there was something else I was going to say about that, but it doesn't matter too much. So here's what I'm going to have you do. Keep working through this. I'm going to walk around and get a sense of where people are before we move on to the next bit. Okay, I'm just going to pause the recording so the YouTube video is not simply just me walking around for an hour. So pause. Is it recording again?
Yes.
Yes, okay, perfect. So for the sake of moving along, let's talk a little bit about this. All right, so We increase the difficulty of the problem. Obviously, if you're looking for bigger numbers, you make the problem more difficult, right? Right now, how big is the search space? Now, when I talk about the search space, I mean, based on our encoding, the representation of zeros and ones of length 10, how many different possible values are there? 1024, exactly. How do you know? Well, because that's how many different combinations of 10 bit. Yeah, 2 to the 10, exactly. Now, I was just talking over there. We got to remember, we've already incorporated information we know about the problem into our representation. The most obvious is, well, what should the encoding be such that it could represent all possible values that would be admissible for this problem? Well, that is a list of zeros and ones of length 10. Makes sense. But I could have also allowed bit strings of length 9, 8, 12 in this. That would have made the search space bigger, but it would also be useless because we know that we want bit strings of length 10. So it would be silly to include bit strings of different lengths, right?
Different smaller lengths.
Smaller lengths or bigger lengths.
If you're specifically searching for a bit strength of like 10, and you find a bit strength of like 11, that's bigger, but you would never have ever found that because you're not even looking at bit strengths of like 11.
But if we included bit strings of length 11, we'd be wasting our time looking at them because they're not going to help us. So we've incorporated information already. Now, if we were looking for bit strings of length 20, or let's say 11, well, now we've got 2,048 different possibilities. As we make the number of bits bigger, and we have our bit strings of length n, the problem gets harder and harder and harder, obviously. How would the number of generations impact the results? Well, you let it run longer, maybe we get lucky and find the better result. This won't be obvious, this won't be clear if the problem is so easy that we find the best result quickly. Okay, yeah, adding more generations is useless, it's wasting time, it's wasting power. But if we've got a sufficiently difficult problem, we might need to let it run longer and longer and longer and longer and longer such that it can find a decent result. How does the population size impact the search? Well, in a similar way. But population size also lets us control a little bit of like the diversity of our population. If our population is very small, the candidate solutions in that population will likely converge faster than if there were more things in the population. And when I say converge, I mean all of the chromosomes start to get more and more and more similar up to the point of being exactly the same. Whenever we see a plot where forget this part here. Ignore this part. I could hit run a bunch of times to find the plot I want, but let's pretend this part doesn't exist. The best result is this, but we can see like the population, the average fitness of the population is starting to match the best. Meaning that that population is converging. They're getting more and more and more similar. And in fact, there's a point where they really are all the same, I'm guessing. They look like they're touching. So the whole population is identical. And when you have a population that's converged, we don't really have, we have no diversity. Crossover won't do anything. We're relying strictly on mutation at that point. So a bigger population could help mitigate early convergence. So that's a good thing. But it also, if we make it too big, we might make it very difficult to exploit what we know is good. Crossover rate. If you have a crossover rate of 0, well, we're not really going to be able to share information around. If we have a crossover rate of 1, we're sharing, everything's getting crossed over every time. You kind of want to balance these things. Same with mutation rate. Tournament size. We already talked about this. As you make the tournament size, if we're using tournament selection, as you make the tournament size bigger and bigger and bigger, as it approaches the length, like the size of the population, if we do that, we're always going to, we're going to be more and more and more likely to pick the best candidate solutions. And we've got to be careful doing that because that'll eliminate any diversity. That'll converge way too fast. If the tournament size is all the way down to 1, well, now we're just randomly selecting, and there's no what we call like selection pressure. Pressure for the good ones to be selected, like the probability of good ones to be selected. I know, like I was saying, 1 is bad. Like 1 is random. Like randomly pick 1, it gets selected. What's the likelihood of me picking the best one? Well, 1 over n, where n is the size of the population, right? If I pick all of them, the probability of picking the best one is n over n, so I always pick the best one. It's funny though, because, I mean, a lot of times, like, even though like 1, that's clearly random, there's not much there, usually people do have really small tournament sizes, like 2, maybe 3. So we actually keep it pretty low. We really want to avoid early convergence. And then elitism. Who here got elitism working? Good. So why do we do elitism? Well, we don't have an example of it here. But, and this isn't necessarily a bad thing. What elitism does, this is a common enhancement that like basically everybody does these days. But you don't have to, and it's not bad not to do it. There's always a chance that look, I've got a population. Imagine we're at generation, who cares, and I've got a population. There exists within that population a best candidate solution. There might be ties, but let's assume there is the best candidate solution. I might not pick it. It may never get selected to go to the next generation, right? It could get ignored. Meaning, the population won't have that, like, the best fitness will actually go down. Elitism is done to make sure that, okay, no matter what, we find the best candidate solution, make a copy of it and put it over here. Maybe we take the best 2 or whatever, some number. Usually you want that to be very low, like 1. But that way, we never lose the best candidate solution. That's all. And this last question there, like what was the best set of hyperparameters found? Well, that's kind of a frivolous question, for lack of a better term. Like, what does that even mean? For a problem like this that's simple, that we know is the best, we know what the best answer is. What's the best settings? Well, the one that finds the best answer, fastest, I guess, right? But when we're dealing with sufficiently difficult problems, a lot of times we're using these optimization algorithms because we know that going and looking for the best answer is not going to happen. It's going to take longer than the universe has existed. It's not going to happen. So we use these algorithms to find a good solution in a reasonable amount of time. So a good solution might not be necessarily the best solution I can find. It could be, how fast can I find a good solution, right? One that learns really fast might be better than one that gets better but ran 20 times longer. It really depends on the situation. So what's good is hard to really answer at this stage. And at any stage, really. It depends on the context of how you're using this stuff. Any questions or interesting observations that you found when playing around with this stuff? Nothing, really? All right, cool. So the next thing I want to talk about, which is something that you basically spoiled last time, you ruined it, is when I said, how do we measure like fitness? How do we determine what's good? And the one that we were going on was, well, what is the actual binary number, like what is the number that represents? But you had suggested, well, really, we know there's something about this problem that we can exploit. I know that good solutions are those that have more ones in it. So maybe what I should do is change the fitness to be how many ones there are. If a solution has more ones, It's better. So this is how we did it, right? Like if these were our chromosomes, which one's the best? Well, clearly this one's the worst. This one's the best because it's the best answer. But like look at these two here, 7, 13. How many ones are there? 1, 2, 3, 4, 5. And this one has 7 ones. Which one's better? Well, in terms of, this is where it gets tricky. No, that's not the right word. This is where we have to be aware of the context in which we're asking what's good. In terms of what our candidate solutions mean, we're looking for binary numbers that represent the biggest possible integer we can find, unsigned integer, right? So in terms of what we are looking for, evaluating the binary number and its integer, like that's what we're maximizing. We're maximizing that. The one that has the bigger number is the better one. But in terms of what we call like the search space, we know that in the search space, the ones that have the candidate solution, or the chromosomes that have more ones, are better. This won't make full sense until we keep going, like anything that you learn, right? The more context you have, the more these ideas kind of come together. But we are changing like the context of how we're determining what's good or not.
Now here's a curiosity question. What would be better for finding the best solution? Evaluating it based on the number of ones or the actual number itself?
Well, that is an empirical question, the one that we say, like anything with evolutionary computation, the better one is the one that's better, right?
Fair enough.
And how do you know it's better is, well, try it, see what was better, figure it out, right?
Look at the other one and say you simply have less value.
Yeah.
I like that answer.
So the bit string 713, like if at the end of the day, you gave me this one because it had the best fitness. This one, if I'm measuring fitness based on the number of ones, this one's better than this one. But this one's better in terms of what I actually wanted. But maybe counting the number of ones will help me get to the better solution in a better way. It's really changing how we're going to travel through the search space. The search space is all possible combinations of zeros and ones, and how is our algorithm going to like move through that space to find the best solution? So yeah. Okay, there we go. Like here's another extreme example. Of these two candidate solutions, there are chromosomes. This one's better. This one's worse. But in terms of what we know about our encoding, which one's actually like closer to the best solution? This one. We only have one thing to change to get there. Where this, I'd have to change a lot to get there. Do you see? Now, there are two words that we're going to use a lot in this course. The phenotype space and the genotype space. This is borrowed from biology. The phenotype, so before, the candidate solutions were based on what they mean in the problem space. The phenotype space. What's the best integer? The binary number represented as an unsigned base 10 integer. But now we were flipping it. If we're counting the number of ones, we're looking for the chromosome that can be compared based on their encodings. That's the genotype space. When you have a representation that is very direct, this is a very direct representation, where the encoding and what it means are very similar. Zeros and ones versus the list of zeros and ones. They're obviously very similar. But you could have problems where the phenotype and genotype are very different. The representation is very indirect. And we'll see a bunch of these as we go. Where was I going with that? So basically here, it's hard to tell, it's hard to really see what the difference is between the phenotype and genotype space with a very direct representation. But if you were to take, I need a volunteer. You're not going to have to do literally anything. Okay, you, stand up. You don't have to come up here. We all can observe him, right? That is a phenotype. He is the representation of himself. We look at that's your phenotype, right? But you have your DNA, right? And your DNA is decoded and it constructed you, right? His DNA is his genotype. Okay? So that would be analogous to like, okay, your existence in your problem space, but your DNA is like your encoding. Okay? So phenotype is what it represents. Genotype is the encoding of what it represents. Cool? Cool. Phenotype, you can sit down. Phenotype, problem space, you did a great job. Phenotype space is the problem space. Genotype is like your encoding space, your problem space. So here is an alternative fitness function. Okay, it's got an exception check. Otherwise, it goes through and counts the number of ones. The more ones, the better. Here, I'm not actually counting the number of ones. I'm just summing up the total of the chromosomes. If there's a 1 there, add 1. If there's a 0 there, add 0. It does nothing. So effectively counting the number of ones. So this is a new fitness evaluation. So what I want you to do is add this to your code. It might already be in what I gave you, so you don't have to copy it. But change out what fitness function your evolutionary algorithm is actually making use of. And play around, and go play around with the hyperparameters like you did in the previous set of things. But go play around with this new encoding, our new fitness evaluation, and see what it does. I'm going to pause the recording again for the sake of everyone watching this later. Okay, now answer the question. Did it work better? Changing out the fitness? Worse? Hard to tell?
Ironically, I thought it would worse.
Interesting, interesting.
I would have expected it to be better, in all honesty.
Did you crank up the problem difficulty? Like, did you make
I
like...
kept it at the base and was just rerunning it a few times.
Yeah.
And I found it never actually really got to 10 that many
Yeah.
times.
Try real quick.
Stuck at 9.
Try running it with the old fitness where you've got n as like 30. And run that. And then use the ones fitness and put n at 30. See what that does. You got to make sure the problem's difficult enough.
Interesting. One's fitness is actually performing better when the n is 30.
The ones, you mean counting the ones?
Counting the ones is performing better than value fitness.
Yeah. Try making n like 100. See what happens. Although, someone might be able to know what's going to happen.
If your computer can handle it, good job.
Well, okay, actually, for the sake of time, because we are running out of time, ask the question, can your computer decode a 100-bit binary number effectively?
Depends on how crappy your computer is.
No, it really depends. It doesn't, you could have the best computer there is. Your computer ain't going to decode a 100-bit binary number. You're going to have an overflow issue, right?
It's working perfectly fine. I'm only getting like half for value fitness every time.
Yeah.
My fitness is
I'm wondering what your actual gets decoded for.
pretty much.
So here's one thing I want us to think about. And this is not something I want you to take too literally, but I want you to think about problem space and coding space. When we're doing the ones fitness, and goodness is a measure of how many ones there are, we can start, here's an example with 3 bits. In one step, by making one change, I can make an improvement, right? To get to like, okay, this is better. And then if I want to get to something better, I can make like another one change. To go from here to here, it's one step. From here to here, it's one step. From here to here, it's one step. And then finally, to get to another one step. It's one step to make one like improvement with the ones fitness. But if we're thinking about it in terms of the phenotype space, if I'm at 0 and I want to go to like 1, okay, that's one step, fine. And then I want to go to 2, where 2 is better than 1, right? Like in value fitness, 2 is one step better than 1. But how many steps do I have to make? How many changes to this representation, this particular chromosome, do I have to make to get to the number 2? 1, 2, or 1, 2, or, well, I can't get there from there, but I have to make 2 steps. So it's actually harder for a 1 increment change. But how many, like the gradient, for lack of a better term, with 3 bits, how many different fitness values are there? 0, 1, 2, 3. But in binary numbers, well, 2 to the power, there's 8, right? 8, 1, 2, 3, 4, 5, 6, 7, 8. So there's actually there's like a better gradient, like there's more steps. It's like a ramp versus like fewer steps. So it's always a bit of a give and take, you know, different things. Now we are way out of time now, a whopping minute, but we're going to pick up here last time where we're going to finish this off a little bit and then we'll carry on with actual topics. The reason I really want you to go through a few lectures like this is I want to make sure we have a chance to really play around with it, ask questions so we know how they work before we keep going. Because once you've got a good sense of GAs, you're great for the rest of the class. All right, I'll see you all later.